We are living in an era where energy is no longer a luxury, but a necessity. As the global population grows and our economies expand, the demand for energy continues to rise. But our current energy sources, mainly fossil fuels, are not only limited, but also polluting. Climate change looms on the horizon, urging us to find sustainable and clean alternatives. In this context, the future of energy is being rewritten with a new chapter: fusion power. Fusion power holds the promise of a clean, safe, and nearly limitless energy source that could revolutionize the way we power our world. It offers an attractive alternative to traditional fossil fuels, which are not only finite, but also have a detrimental impact on the environment. By harnessing the same process that powers our sun, fusion power could provide us with a virtually inexhaustible supply of energy without the harmful emissions that contribute to climate change. But what exactly is fusion power, and how does it work? How close are we to harnessing this powerful energy source, and what challenges must be overcome to make it a viable option for the world? Join me on this journey as we explore the depths of fusion power, unravel its mysteries, and discover how it has the potential to shape the future of our planet. What is the problem we face today? Our current energy needs are met primarily by burning fossil fuels such as coal, oil, and natural gas. However, these resources are not only non-renewable, but also finite. We're rapidly depleting them at a rate much faster than they can be replenished naturally. This raises concerns about energy security and the sustainability of our energy production methods. Moreover, the combustion of fossil fuels releases harmful greenhouse gases into the atmosphere, contributing to global warming and climate change. These emissions have a detrimental impact on the environment, leading to rising sea levels, extreme weather events, and disruptions to delicate ecosystems. To address this pressing issue, we must explore alternative energy sources that are not only clean, but also capable of meeting our growing energy demands. Fusion power presents itself as a beacon of hope in this regard. Unlike fossil fuels, fusion power harnesses the power of nuclear fusion, the same process that occurs in our sun. It involves fusing lightweight atoms, typically hydrogen isotopes, to form heavier ones. This fusion reaction releases tremendous amounts of energy without producing greenhouse gases or long-lived radioactive nuclear waste. Furthermore, the fuel for fusion power, hydrogen, is widely available and can be extracted from seawater. This abundance of fuel ensures that fusion power could potentially provide a limitless supply of energy, alleviating concerns about resource depletion. However, despite its numerous advantages, achieving practical and commercially viable fusion power has proven to be a formidable challenge. One major hurdle is the difficulty in reaching the extremely high temperatures and pressures required to initiate and sustain the fusion reaction. Another significant challenge lies in maintaining the stability and confinement of the hot plasma, which contains the fuel for the reaction. Additionally, the complexity of the technology involved in developing a fusion reactor leads to high costs and economic barriers. For decades, scientists and engineers have been working tirelessly to overcome these challenges and bring fusion power within reach. Significant progress has been made, particularly with large-scale international collaborations like the International Thermonuclear Experimental Reactor, ITER, which aims to demonstrate the feasibility of fusion power. While the path to commercialization is still uncertain, the potential benefits of fusion power make it an enticing prospect for powering our future. So what is fusion? At its core, fusion power generation involves a nuclear reaction known as nuclear fusion. This is the same process that powers our sun and other stars. In fusion, two or more atomic nuclei combine to form one or more different atomic nuclei and subatomic particles like neutrons. The difference in mass between the reactants and the products manifests as either a release or absorption of energy. This is because mass is converted into energy, as stated in Einstein's equivalence of mass and energy. In the case of our sun and other similar stars, the light elements involved are hydrogen and helium. Hydrogen nuclei fuse to form helium, giving off energy in the form of light and heat. Now let's delve into the details of how fusion power works in a bit more depth. First, we start with the fuel, which primarily consists of deuterium and tritium, isotopes of hydrogen. These isotopes are chosen for their favorable fusion characteristics. The fuel is first converted into a plasma state, which is a superheated and electrically charged gas. This plasma is then confined and heated to extremely high temperatures, reaching millions of degrees Celsius. At these high temperatures, the positively charged nuclei of the hydrogen atoms overcome their natural repulsion and come close enough together for the strong nuclear force to take hold. This force binds the nuclei together, forming helium and releasing tremendous energy in the process. To achieve and maintain these extreme conditions, various methods are employed, such as magnetic confinement or inertial confinement. Magnetic confinement, as seen in tokamak reactors, uses powerful magnetic fields to contain the plasma. On the other hand, inertial confinement, often used in laser fusion, uses high-powered lasers to heat and compress the fuel target. The energy released from the fusion reaction is captured and converted into electricity, which can then be used to power our homes, industries, and transportation systems. Why is it important? Fusion power holds immense importance for various reasons. Firstly, it offers a virtually limitless supply of energy, as the fuel for fusion is readily available in seawater. Unlike fossil fuels, fusion power does not produce greenhouse gases or long-lived radioactive waste, making it an environmentally friendly energy source. It also has the potential to significantly reduce our dependence on fossil fuels, enhancing energy security and reducing the associated geopolitical tensions. Now let's talk about some recent breakthroughs and progress in the field of fusion power. There have been several remarkable advancements that bring us closer to harnessing this clean and sustainable energy source. One notable achievement was the record-breaking plasma temperature reached by the Joint European Torus, JET, a tokamak reactor in the United Kingdom. In December 2021, JET successfully generated a plasma temperature of 316 million degrees Celsius, surpassing the previous record of 272 million degrees Celsius set in 1997. This breakthrough demonstrated the potential of magnetic confinement fusion and provided valuable insights into the conditions required for sustained nuclear fusion. Another significant development occurred in December 2022 when researchers at the National Ignition Facility, NIF, at the Lawrence Livermore National Laboratory achieved a net energy gain for the first time. This means that the amount of energy produced from the fusion reaction exceeded the amount of energy required to trigger the reaction. This milestone was a testament to the hard work and dedication of the scientists and engineers involved in the project. More recently, smaller-scale molten salt thorium reactors have shown promise as well. These innovative reactors offer several advantages, including enhanced safety features, improved efficiency, and the ability to use thorium, a more abundant material than uranium as fuel. For example, the pilot plant in China has successfully operated for over 10,000 hours, demonstrating the viability and reliability of this technology. Despite these impressive achievements, there are still many challenges that need to be addressed before fusion power can become a mainstream energy source. One major hurdle is the cost and complexity of building and maintaining fusion reactors. These reactors require sophisticated technology and advanced materials that drive up the overall cost. Another challenge lies in the difficulty of achieving and sustaining the extreme temperatures and pressures necessary for fusion reactions. Additionally, the low energy yield per unit mass of fuel compared to fossil fuels requires careful consideration. ITER, the largest and most ambitious fusion experiment to date, is an international collaboration aimed at demonstrating the feasibility of fusion power. Located in France, ITER will use a tokamak reactor to confine and heat plasma to extreme temperatures, producing a net gain in energy. The project involves 35 countries and is expected to begin operations in 2025. Once operational, ITER will serve as a platform for testing various technologies and components related to fusion power. Its primary objective is to demonstrate the scientific and technological feasibility of nuclear fusion as a viable energy source. Significant private sector investments are also driving progress in fusion power. Companies like Commonwealth Fusion Systems, Helion Energy and General Fusion are developing innovative approaches to fusion power. These startups are attracting substantial investments and fostering competition, which accelerates innovation and advancement in the field. For instance, Commonwealth Fusion Systems has developed a compact tokamak design that promises to deliver net carbon-free energy in the 2030s. Several countries worldwide have recognized the potential of fusion power and are actively pursuing research and development efforts. China, for example, has invested heavily in fusion research and has successfully operated several experimental reactors, including the experimental advanced superconducting tokamak, EAST, which has achieved record-breaking plasma confinement times. India, through the Institute for Plasma Research, is actively engaged in fusion studies and is collaborating with international projects like ITER. Similarly, Japan's JT60SA tokamak reactor is contributing valuable data to the international effort to achieve net energy gain. These national initiatives are crucial for advancing fusion technology and bringing it closer to commercialization. When can we expect fusion power to be available commercially? The timeline for the commercialization of fusion power varies depending on the progress of ongoing research and development efforts. Some estimates suggest that it may be possible to have small-scale commercial fusion plants by the 2030s. This timeline is based on the assumption that current experiments like ITER are successful in demonstrating the feasibility of fusion power and that private sector companies continue to make significant advancements. It's important to note that fusion power is a highly complex and challenging endeavor. There are still many scientific and technological hurdles to overcome. Therefore, it's possible that the timeline for commercialization may extend beyond the 2030s. Overall, fusion power holds immense potential as a clean, safe, and nearly limitless energy source. It offers an attractive alternative to fossil fuels and could significantly contribute to reducing greenhouse gas emissions and mitigating climate change. While there are challenges associated with achieving and sustaining nuclear fusion, recent breakthroughs and advancements bring us closer to realizing this dream. Continued investment, research, and international collaboration are essential to unlocking the full potential of fusion power and paving the way for a more sustainable and energy-secure future.